So it looks like we are already live. So hello everybody, and I'm glad to greet you actually on the first event of Ukrainian Scientific and Educational IT Society. So we are going to invite different distinguished computer science academics all over the world. Before we'll start and before I'll invite our today's speaker, I will stop on some technical issues, so please turn off your microphones. You can use chat for any comments, but if you have a question, I'll ask you to use Q&A section. Also, for those who are watching us on live on Facebook, you can also ask your questions in comments. And I'm glad to give a floor to Melanie Mitchell, professor at the Santa Fe Institute. So Professor Mitchell has worked on artificial intelligence from fascinating perspectives, including adaptive complex systems, genetic algorithms, and cognitive architecture. Professor Mitchell is the author of 6 books and numerous scholarly papers in the field of artificial intelligence. So, Professor Mitchell, the floor is yours.
Great. Thank you so much for inviting me to speak at this event. Can you see my slides okay?
Yes, perfectly.
Okay, perfect. So I'm going to talk about a very prominent debate that's going on in the AI community that I wrote about with my collaborator, David Krakauer, and was published recently in Proceedings of the National Academy of Sciences on whether large language models can understand in any interesting and meaningful sense. So I'll talk about what that means. So we know that many AI systems have been shown to have trouble understanding the data that they process, at least in a human-like way, and that it matters because these systems can make errors that are hard to predict and that might have big impacts on the people that use these systems. So here's a few examples. Way back in 2018, when people were using deep neural networks to do very well on the ImageNet object recognition challenge, we had deep neural networks that were able to recognize objects like this one, school bus, with 100% confidence. But this group showed that if these objects were rotated via Photoshop or other photo apps in different poses, then the network was 99% confident that this was a garbage truck or a punching bag, 100% confident, or a snowplow, 92% confident. So these networks were seeing these images confidently in a very different way than humans were. And so the systems, while they seemed to do very well on images that were similar to ones they'd seen in their training data, actually had a lot of problems when the images were changed in some way that humans would not find so puzzling. We've also seen examples more recently of things like self-driving car vision systems that do very well on recognizing objects on the road, like cars, but have trouble distinguishing, say, images on the back of a van that's an advertisement for e-bikes here, recognizing these images as real things in the road, like bicycles and people. So being able to take into account the context of an image seems to be a challenge for a lot of these vision systems. And one very striking example of this was when this person tweeted that his Tesla that was using the self-driving software kept slamming on the brakes in this area that had no stop sign. But after a few drives, he noticed this billboard, which if you scale it up, you can see is an ad for something, I don't know what, but there's a police officer with holding a stop sign, and the car was interpreting that as a real stop sign and slamming on the brakes. So this kind of basic recognition of context and common sense knowledge has been very challenging for AI systems. Another example of a lack of understanding is in when AI systems, machine learning systems, learn what's called shortcuts. So one example is in this paper, these researchers trained a deep neural network to recognize skin cancer, malignant skin cancer. And when they, their system did very well on a particular benchmark of images, but they found when they looked at what cues the system was using, that images that contained rulers, like this ruler, were more common to be seen in malignant skin cancers than in benign skin cancers. And the system had been using rulers as a predictor for skin cancer because, of course, it had found this statistical association. This is called a shortcut, where the machine learning system learns something that is useful for predicting something that makes it do well on the training data, but that thing that it's using is not what we intended it to use, and it won't generalize well. Here's an example that Dimitro gave me for you. I had, in my earlier talk, I had an example in French, but he gave me this example in Ukrainian of Google Translate translating an idiom, an English idiom. We wanted to play football, but now it's raining cats and dogs, so I guess we'll stay inside. And the Google Translate was really not understanding the context of this idiom and translated it quite literally into Ukrainian. So I'm sure, I actually don't know what this says, but you all can see that example. So this actually has had, this kind of translation error has had real world effects. For example, people working in processing refugees applications for the US, asylum cases, have found that the translation apps they're using can make very big errors that can actually endanger some cases. So now we're really in a new era of AI with large language models like ChatGPT. And some people have proposed that these systems are really a revolution in AI that have achieved a richer human-like understanding than the previous AI systems, which I showed you can often be quite brittle. So here's an example that Dimitro gave me from ChatGPT. It asks ChatGPT to translate from English to Ukrainian the same sentence. And here's its translation, which is much better than what Google Translate gave us. And you can even ask it to explain the translation, and it explains it. It says it means made sure to convey the same ideas while adjusting the idiomatic expression appropriate for the target language, and talks about how it's translating this idiom into the Ukrainian idiom, which is really expressing the same thing. So it does seem to understand this language much better than previous AI systems ever have. Terence Sinofsky, who was a pioneer in neural networks going back as far as the 1980s, wrote this paper saying that, you know, something's happening now that we didn't expect. These systems can communicate with us in an eerily human way. They're not human, but they're superhuman in some aspects. And some aspects of their behavior appear to be intelligent, but if it's not human intelligence, what exactly is the nature of their intelligence? And this is something that everybody in the AI community is grappling with. How do we characterize the nature of the intelligence of these systems? Some people have proposed that, for instance, these systems do, in a very real sense, understand a wide range of concepts. Blaise Aguirre-Arcas is a AI researcher and a vice president at Google. And he's very much believes that these systems do understand language. But people like Jacob Browning and Yann LeCun, who's the head of AI at Meta, take an opposite view. They say that the systems trained on language alone will never approximate human intelligence and understanding, even if trained from now until the heat death of the universe. So this is really a big debate in the AI community. And one group did a survey of natural language processing researchers, asking people who attended big NLP conferences this question: do you agree or disagree? Some generative models trained only on text, given enough data and resources, could understand natural language in some non-trivial sense. And the results of the survey were really split down the middle. 50, here we have, the people who weakly disagree, weakly agree. And really it's just half and half, which shows that there's no agreement in the community on this question of understanding. So how is it that we can evaluate whether LLMs understand? Well, one way is to just look at their behavior, have a kind of a Turing test where you just talk to them, and do they seem like a human? Could they fool you into thinking that they're human? Well, one problem with that is called the ELIZA effect, named after the original chatbot, ELIZA, from the 1960s, which mimicked a psychotherapist. And people talked to ELIZA. It was very primitive, but they talked to it, and often they were convinced that it understood them and that they were talking to some entity that actually had intelligence and understanding. So humans are very prone to project understanding onto systems that communicate in natural language. And this is something we have to be aware of, that we ourselves can be fooled. So a more objective approach is to test these systems on benchmarks that try to assess natural language understanding. And there's quite a few of these benchmarks in the NLP community. But the problem is that such benchmarks often allow the kinds of shortcuts that I showed before, where there's subtle statistical associations in the text that allow the system to do well on the benchmark without actually understanding in the way people do. So, for example, there's a data set called the GLUE, the General Language Understanding Evaluation, a collection of natural language understanding tests, and its successor, SuperGLUE, which is even more extensive. And here is the leaderboard, which shows the scores of different systems on this benchmark. The top 7 are all large language models. Number 8 is humans. So does this mean that these large language models outperform humans at language understanding? Well, on these benchmarks, yes, but it's unclear that these benchmarks actually truly test language understanding due to issues like shortcuts. And people have talked about this kind of thing in many different papers. And I think it's often it's very subtle to tease out exactly what these shortcuts are. Another approach is to give these large language models standardized tests that are designed for humans. So we've seen headlines like ChatGPT does better than many students on MBA exams or law exams or medical licensing exams. But the problem is that it's hard to know whether parts of those exams or something similar were actually in the system's pre-training data. That's called data contamination. We don't know what the pre-training data is for systems like ChatGPT. So it's hard to know if they were actually trained on something similar to the things they're being tested on. But also, it's not clear if performance on these kinds of tests for a system that's sort of memorized the entire internet in a way, will actually correlate with performance in the real world on new kinds of questions that aren't like ones they've seen before. And I wrote about this in my Substack blog, and other people have reevaluated the performance on different standardized tests and shown that it's less impressive than it originally seemed. And others have argued that the professional benchmarks designed for humans are not appropriate for testing these large language models. So now another approach is to evaluate these systems on tasks that require what we feel like are the sort of hallmarks of understanding, the ability to abstract and to reason. But even when these systems do well on reasoning tasks, there's a question of how real or robust are the abstractions they create. So as one example, this paper did a test on a whole bunch of different tasks that required some kind of abstraction and reasoning, and showed that when given questions in each domain that were similar to what's likely to be in the training data, GPT-4 did very well. That's these blue bars. But when they changed the task to be what they called counterfactual task, different from what's likely to be in the training data, but using the same abstract reasoning processes, the performance of GPT-4 went down fairly dramatically in many cases. So just as one example on code execution. So GPT-4 is quite good, you can see on this blue bar, of the task of taking a little snippet of Python code and printing out what it would produce when run. So it interprets the code, and in some sense understands the code. And this is, the prompt, the kind of prompt that's given. But these researchers said, well, what if we make a counterfactual task where we have this pretend hypothetical programming language, they called it ThonPy instead of Python. It's identical, except structures like lists, like this one, are indexed by 1 instead of 0. So rather than this being the 0th element, it's the first element. So, this is something like MATLAB and R. The indices start from 1. Can you then print out what these snippets of code do? And there, this sort of red bar shows that GPT-4 was much worse on that version, was not able to adapt what it understood in the original case to this new, very similar case, whereas I think any human programmer who understands code would be able to adapt it. So that's a kind of abstraction that GPT-4 doesn't seem to be able to make. Another paper, there's been several papers on this same theme. This paper called Embers of Autoregression showed that when they tested in various reasoning problems, so GPT-4's performance on things that are likely to be common in the training data the performance was much better than when they tested the same reasoning task, but with content that was likely to be rare in the training data. So the take-home message here is that large language models tend to be better, often dramatically better, on solving reasoning tasks that are similar to those seen in the training data. And that reflects a failure of abstract understanding. So how is it that we could get machines to learn and use human-like concepts and abstractions? This is really the topic of my own research. Well, human concepts are mental models of categories, situations, events, and even one's own self and internal state. So how can we get machines to form the kinds of mental models that we humans use to understand? So here's a really simple concept: on top of. So something being on top of something else. Okay, basic spatial concept. Okay, well, we know that human concepts are compositional. If you understand something on top of something else, you can understand something else on top of that and something else on top of that, that we can build up, this notion of on top of to apply sort of recursively or iteratively. If we understand something like a cat on top of a television, we can also understand a television on top of a cat. Okay, this I got DALL-E, the text-to-image program, to generate, but it had a lot of trouble generating a television on top of a cat because that's much less likely. But humans are able to take these compositional concepts and apply them in different ways. They also have causal structure, and they enable us to predict, to reason, and to have basic common sense. So even babies learn if things that are on top of other things, how those things will behave under certain kinds of interventions. Children can reason about how to get on top of something that they want to get on top of, and also learn sort of the topological reasoning. For instance, shoes go on top of socks, so you have to put your socks on before you put your shoes on. Okay, so humans are able to understand these very basic ideas. Moreover, concepts like spatial concepts can be abstracted to new situations via analogy and metaphor. So, in English, we have all these metaphors that use this concept on top of, like on top of the world, on top of one's game, at the top of one's voice, translating the spatial ideas to more other modalities and more abstract situations on top of a social hierarchy. So this is something that's absolutely central to, I think, our human understanding, is this ability to take concepts, basic concepts, and abstract them in this way. And in fact, the cognitive psychologist Lawrence Barsalou defined a concept as a competence or disposition for generating infinite conceptualizations of a category. And you saw how I was trying to get at that with this concept of on top of, but really you can do this with any concept. And it's really saying that what concepts are mental models that are generative. And I think this is something that's really needed in AI. And Lakoff et al. Proposed that abstract concepts are learned via metaphors involving core concepts. So, for example, we conceptualize social interactions in terms of physical temperature. We say things like, she gave me a warm greeting, or status is conceptualized as physical location. She's 2 rungs above me on the corporate ladder, things like that. So Lakoff et al. have shown this is just pervasive in our language, this understanding of abstract concepts via metaphor. So other people have proposed that concepts are grounded in mental simulations of physical situations. So people like Josh Tenenbaum and his collaborators proposed that our physical understanding and metaphorically our abstract understanding is grounded in actually mental simulations, kind of like game engines. And they talk about the notion of the game engine in the brain, that we actually do some kind of simulation of physical properties in our understanding. And finally, Liz Spelke, a developmental psychologist, proposes that this concept learning builds on innate systems of what she calls core knowledge. And core knowledge is what she proposes is essentially innate in humans, that we're born with either knowledge itself or a strong propensity to learn this kind of knowledge about, for instance, objects, that the world is divided into objects and objects have certain kinds of interactions. Numerosity, we understand concepts like something being larger than something else or smaller, some we know about very small numbers like 1 and 2. We sort of understand those kinds of concepts and build upon that. Basic geometry and topology of space, and we understand things like certain kinds of relationships, like things are inside other things or outside, certain things contain other things, and so on. And we also understand about agents that have goals and that certain kinds of behavior can be goal directed. So this is a proposal for how concepts arise and how they are built up out of these basic core knowledge systems. So how do we get machines to understand in all these various ways that I've been talking about these kinds of human-like concepts? Well, Francois Chollet, who's a researcher at Google, proposed what he called the abstraction and reasoning corpus. He proposed it in this paper, which I recommend if you're interested in AI and cognitive science. It's a really interesting sort of argument about how to measure intelligence in either humans or machines. And he proposed this benchmark, essentially, which is a domain for concept induction and abstract reasoning. And it was inspired by Spelke's core knowledge systems. So let me just give you an example. So this is called a task in this abstraction and reasoning corpus, or ARC. Here, the world is defined in terms of grids with colored pixels, and one grid is transformed into another. So this is an example of a concept. Okay, so this one transforms into this one. Here's another example. This second one transforms into this one. A third example, this bottom one transforms into this one. So all of these transformations have something in common, and that's sort of the abstract concept that the task is demonstrating. And your task is to do the same thing to this test example. Okay, clearly, what I think you can probably see the pattern. You take the color that's sort of different in this little pyramid, and you extend the sort of pointy part of the pyramid to the boundary with that color. So here we would do that with this light blue up to the top. So this involves concepts of objects, of shapes, of different color, of extending something to a boundary, of directionality, which way this is pointing, all kinds of these sort of core knowledge concepts. Okay, here's another one. Okay, so we have 3 demonstrations of transformations, and your task is to do the same thing to this new test example, this test input. And if this were an in-person talk, I'd ask for volunteers to tell me, but I'll just tell you here. So here, this is a sort of about shape invariance. So we have these different kinds of shapes, this kind of a rotated U shape where, and those shapes are colored pink, no matter what size they are, no matter what direction they're facing, no matter where they are in the grid. And similarly, these kinds of shapes that look kind of like well, this one's another U. This one looks like an L rotated, it's colored blue, and the ones that look like backward H's are colored red. So this notion of shape invariance is an important idea having to do with how shapes can be transformed in various ways. So Cholet created 1,000 different tasks that tried to get at understanding core concepts and being able to abstract the concept to understand the concept with just a few examples, right? So you can think of these in machine learning terms as 3 training examples and a test example. So it's a few, what's called a few shot learning problem. There's only a few examples. Humans are very good at that, but machines are not so good at this. So he published 800, he held out 200 as hidden test set, and he put the whole challenge on the Kaggle platform. Kaggle is a platform for machine learning challenges that people compete on. In the end, he offered some prize money. In the end, about almost 1,000 teams submitted programs that attempted to solve this challenge, and they were tested on the hidden test set, and the winning program got about 20% accuracy. And each program was allowed 3 guesses per task. And if it got one of them right, the task was considered solved correctly. So given that, the winning program, which was a program synthesis approach, tried to, given that the demonstrations tried to synthesize a program that would generate these transformations and then to apply it to the test. So it only got about 20%. The ensemble of the top 2 programs got about 31%. This is the world record. And there's a new challenge. There was a challenge last year run in Switzerland where you could earn 1,000 Swiss francs, which is about $1,000 for every percentage point above the world record. And I think the new world record is about 34% accuracy. So, and there's a new Arcathon challenge in 2024. So still this, this is much lower than human ability to solve these problems. And people have tested large language models as well, and I'll talk a little bit about this. So our group, my collaborators and I here, felt that this was a fantastic challenge. We really liked it, but it had a few problems. Many of these problems in the original ARC task were actually pretty hard for humans. And also they didn't systematically test understanding of concepts. So just as an example, if a program can solve this task correctly, does it mean that it understands in a general sense the notion of object invariance? Well, not necessarily, because it might be using some kind of shortcut. There might be some shortcut, like, I don't know if that's true here, but maybe the things with the most the things on the left tend to be red and on the right tend to be blue. That's not the actual shortcut here, but there might be other shortcuts that are enable you to solve a particular problem. So really what you need instead is a whole bunch of variations on each concept. So this is work that I did with some collaborators here at the Santa Fe Institute. We created this new benchmark called Concept Arc, where we created variations on ARC tasks for each of 16 concepts, and we tried to make them as easy as possible for humans. But for each concept, the tasks varied in complexity and degree of abstraction. So the kinds of concepts we looked at were spatial concepts like identifying something at the center of something, inside versus outside, same versus different, that's semantic concept, top versus bottom. So let me give you an example. We had a total of 480 tasks. Each concept group, like center, had 30 different tasks. So here's a pretty simple example from our benchmark. So here you probably can see easily the task is delete the bottom object, whatever that object is, to get from the left to the right. And then do the same thing here on the test input. Okay, well, we tested humans on this. We also tested the winning program from the original Kaggle competition, and we tested GPT-4. We actually tested GPT-4 in two ways. One was using sort of a text version of these tasks where you give each pixel as a number. You just give kind of the pixel values of the each grid. And we also tested it using its vision system, where we actually give the actual grids to its vision system. I can tell you later exactly how we tested it, but we found that the text-only version worked a lot better than the vision system, interestingly. Anyway, all of these systems got this correct. So does that mean that all of these systems, humans, this Kaggle program, and GPT-4 understand top versus bottom and objects? Well, we have to test it further. Here's another variation on that same concept. Here, the rule is color the top row of the object red. Okay, everybody got that right. It's looking good. But if we give yet another variation, remove the top and bottom objects. Here, 100% of humans got it right, but these programs got it wrong, showing that they lack some robustness in this concept of top and bottom. And, here's another example. This one says, extract the center pixel color. Okay. Most humans and the programs got that one right. But this one, another one, extract the center object. Humans 100% got that right, the winning program, and GPT-4 got it wrong. And this one is another variation. Move the colored pixel to the center and extend it. Humans got that right. These programs got it wrong. And this was another, when we compared humans and these systems on these tasks. Here are all the different tasks. There's 30 different, all the different concepts. There's 30 different tasks per concept. And here's human performance, very high overall. The first place Kaggle program, now this is higher than the 20% that it got on the original ARC benchmark, because our problems are intentionally much easier. And here's GPT-4's best performance. So these programs are still lagging behind humans on these relatively simple conceptual abstraction problems. Here, I'll skip that. So just to end, my question was about the debate over understanding in language, and I think also just in general, understanding the world that language describes. In principle, I think AI could understand the world. You know, we humans can understand it to some extent, and I don't see any reason why we couldn't build AI systems to do that. But current AI still has many failures of understanding, which makes it untrustworthy in many cases. And I believe that to understand the world in a human-like way, we need to give these systems human-like core knowledge systems and concepts, you know, that I talked about extensively, how we humans build up these concepts. And these are all abilities, composition, analogy, metaphor, causality, that current AI systems lack. You know, current AI systems have kind of gone backwards. They start with language and they supposedly can get emergent concepts from that. Whereas humans, as babies, start with learning concepts, basic concepts, and then build language on top of that. So AI is learning in an opposite way as humans, and it might not be the best way to learn robust systems that understand the world. And I don't know, you know, some people have proposed that AI systems will need something like embodiment or active interaction in the real world, as opposed to just learning from language or passively learning, you know, being given images or videos. That's a real big question that I think we can explore empirically. So I'll stop there. This was our paper in PNAS that talked about a lot of these issues, and I'm happy to answer questions and have discussion. So thank you.
Thank you. So it's time for questions. We have some questions in chat and in QA section. But actually, if you want to ask your question out loud, you can just raise your hand, and I will give you a turn. So the first question from the chat: can an AI simulation of understanding then distinguished from genuine understanding, and does the distinction matter for practical applications?
Yeah, I mean, I think that is sort of a philosophical question, whether a simulation of understanding is different from actual understanding. I think that's what, you know, the Turing test was meant to get at, that question, and say there is no difference. If behaviorally a system acts like it understands, then it does understand. That was kind of Turing's point. But as I mentioned, that actually, you know, runs into problems with the so-called ELIZA effect, that we humans can be easily fooled. So, you know, I don't know the answer to that question. I think that right now, it's still not that hard to distinguish machines from humans if we really are trying to do that. You know, machines can fool us if we're not really trying to distinguish them from humans. But if we actually are giving a very more rigorous test, we can tell if something, you know, if something's a machine or not. But in the future, maybe that will change. And in that case, you know, it's going to be harder to say whether or not we believe they understand without actually better defining what we mean by understand, and like looking internally at, do they have the kind of mechanisms that we believe underlie understanding?
Thank you. Eduard, do you want to ask a question with voice?
Yes. I would like to ask a question by voice, because it seems to me that we don't have a good definition of understanding. So we talk about if these big, huge large language models understand, or in general in natural language processing, we don't have a good definition of understanding. And I want just to offer an argument that any AI system cannot understand, because it cannot have experiences like us. So imagine I say I like ice cream, right? I do have an experience of tasting an ice cream. But all these artificial intelligence systems cannot have this experience. They don't have qualia, and therefore they cannot understand. So you might try first to define what understanding is, because we are not sure what we are looking for. So I would like your take on this. I think it's a philosophical problem. It goes back to the Chinese room argument of John Searle, but there is now a resurgence of experience in neuroscience with Christoph Koch. For example, he's talking a lot about this experience of humans, in the fact that the computational system cannot encompass this experience. Thank you.
Yeah, as you say, that's a, philosophical question about sort of sentience and consciousness and embodiment that has been argued for probably for centuries, even before AI. So I agree with you that the question of understanding is not well enough defined for us to answer the question. So maybe one of the things that AI is forcing us to do is to think about different kinds of understanding, to make the definition more sort of dependent on what type of understanding we're talking about. And I think that AI is also forcing us to think about words like intelligence and consciousness and all of these mentalist terms that don't have rigorous definitions. Perhaps we are going to have to redefine them, at least intuitively, to make room for machines doing what they do, that perhaps they understand in some ways, but not in others.
Thank you. So we have also some questions in Q&A section. The first question, can we ask your opinion about intelligent systems on the Android platform? For example, expert systems that can correctly justify their decision about a problem compared to ChatGPT. And according to your talk, ChatGPT doesn't justify its decision quite correctly. Is it possible in the future to use not only ChatGPT 4, but also other LLMs for decision making?
So, yeah, I think, there's always been a bit of a trade-off in machine learning over performance versus interpretability. That systems, like, for instance, in machine learning, we have things like decision trees, which are much more interpretable, more symbolic kinds of systems, versus neural networks, which are not very interpretable, but perform much better in general. So it may be, and many people have proposed, that we really need to merge these kinds of approaches to have what are called neurosymbolic systems that retain the sort of performance of things like deep neural networks, while allowing the more symbolic approaches to interpretability. I think it's a great idea. We haven't really seen it work very well yet, but perhaps in the future that will be the kind of system we rely on in these hybrid systems. So yeah, I think it's an area of very active research. That's all I can say for now.
Great, thank you. So the next question from the chat about the experiments. Is the IQ of people who participate in tests assessed? Is the speed of the correct solutions found assessed? How many attempts are given to people, and are people selected based on their IQ or age or any other criterion?
Yeah, so in the experiments we did them on this site called Prolific, which is a sort of crowdsourcing site for doing, like, psychological experiments and other tasks for humans. All we asked was that people be over 18 and speak that English was their native language for these particular tests, because part of the test was to ask them to write explanations of how they solved the problem. We did not collect information about the speed by which they solved the problem. We gave each person 3 attempts, just like the programs to solve the problem. And we didn't give them any feedback except that they didn't get it correct the first time or the second time, perhaps. And that was the same feedback we gave the programs. I think that was all the questions.
Okay, thank you. So we have two more philosophical questions in Q&A. So how do the differing interpretation of understanding among AI researchers reflect broader philosophical disagreement about the nature of intelligence and cognition? And I think that we can also put the second one. How might LLMs influence our understanding on human language processing and cognition?
Okay, yeah, those are two really great questions. Yeah, I think that there's a lot of difference in philosophical approaches to understanding, which is probably what makes this debate. So as was previously brought up, maybe having this notion of qualia, this like, what does it feel like to eat an ice cream, or what does it feel like to see the color red, that without having a body and then the right kind of sensors, you can't understand that. That's one proposal, but other people, feel that at least a good enough kind of understanding can be gleaned just from language alone. That's I think that's really a difference of opinion in this. The second question was, how can these LLMs sort of affect our view of natural language? And yeah, I think it's really challenged a lot of theories of how, natural language works and how it can be learned. There was, the most influential linguist, of course, is Noam Chomsky, who saw language as, you having to have some kind of innate structure that's sort of what he called universal grammar was necessary. And it does seem that large language models, which do not have that kind of innate structure, have captured the syntax and often some of the semantics of language. So it does seem like that kind of hypothesis has been strongly challenged, if not disproven. So there's still some debate about that too. So I think these things, one of the things that AI has done throughout its history is to challenge our views of how intelligence works. And large language models perhaps are some of the biggest challenges.
Okay, thank you. And I believe I have the last question. Considering the current trajectory of AI development, how should we prepare for the integration of AI into society, especially in roles that traditionally require deep understanding and empathy?
Yeah, that's a hard question. I mean, AI, we've already seen a lot of issues in integrating AI in society, things having to do with disinformation, deep fakes, very convincing generation of text, images, videos, audio. That's really having a big effect on how trustworthy media is. And I think it's just going to get worse. And it's hard to know how to solve this problem. There's been a lot of regulation of AI, like in the EU, some in the US, some in other countries. And it's hard for regulators to keep up with the speed of progress or of change in these technologies. So I think it's a really difficult question. In terms of, I think they asked about sort of things that need deep understanding and empathy and so on. Yeah, I don't think humans are going to be replaced as soon as some people say. There's been a lot of predictions about certain kinds of jobs that people have predicted will be replaced soon, and all of these predictions ended up failing. So I'm not so convinced that AI, I think we tend to underestimate how complex human intelligence is and how much unconscious intelligence is needed to do certain kinds of tasks. We certainly saw that with expert systems, where people tried to extract knowledge from experts and put it into a set of rules, and turned out that the experts weren't able to communicate some of the most important things about how they were solving problems and making decisions, because it was sort of unconscious and based on very basic, perhaps non-linguistic knowledge. So it's hard to predict what's going to happen, but I think that, AI is somewhat hyped right now and is not going to have the kinds of sort of effects of killing off everybody's jobs that some people are proposing.
Great, thank you. Actually, I can recommend to our participants to watch Monk debates on AI, where you have participated. And actually, I didn't want to make a spoiler, but we will have one of the speaker who was opposing you in that Monk debate. I wouldn't say who will be yet, but we'll have it in a month. And we have one more question. When will AI capabilities exceed humans, in your opinion?
I think it will be longer than many people have predicted. Human capabilities, I mean, it's hard to say what those are, just, to make a list. So, maybe ChatGPT can like write a paper for you, but it's not going to go fix your plumbing anytime soon. And it's not going to, do a lot of things that humans can do, that, some of which aren't necessarily considered part of quote unquote intelligence, but actually are deeply important for all of our sort of, I think, intelligent related abilities. So I would say not very soon.
Okay, thank you. And we have one more question. Actually, we have 2 more minutes. So the question is to continue the previous question about your experiments. So 100% people solved the tasks within 3 attempts. Were tasks so easy? What happened if somebody failed with 3 attempts? Those results were not used in the analysis. The core of my question is whether we compare the work of AI with the best humans or with the average level of concept understanding. And maybe I can continue that. Actually, we also have seen that ChatGPT successfully passed like law school tests or MBA entrance exams. So maybe we should look also on the tests for humans. Maybe they're not correct, actually.
Yeah. I mean, we in our experiments were really, in some sense, comparing with average humans over our sample. We weren't comparing with the best humans. That's always a question. How do you compare? But we were trying to see sort of on average, are humans able to solve these kinds of problems fairly easily? And generally they were, on these crowdsourcing platforms, the signal is kind of noisy because like some people aren't even trying, right? So, but overall we got pretty high performance from humans. Standardized tests like the bar exam and medical exams and so on do have potential sort of shortcuts. And, humans often can solve them via shortcuts. If you've ever taken a multiple choice exam, you're probably using not just your understanding of the content, but also your understanding of how multiple choice exams work. And I think that, that's kind of a shortcut. But machines are much better at finding very subtle shortcuts. So I'll just say that.
Great, thanks a lot. It was really interesting. For our participants, I want to mention that we'll have a recording of that lecture because we understand the problems with electricity in Ukraine. Thanks a lot. It was Professor Melanie Mitchell. Thank you for your talk, and please subscribe to our social media. We will announce our next talks there. Thank you.
Great. Thank you so much for coming. Bye-bye.